control element it is to adjust to new value. The time for process control loop to make necessary adjustment to final control element is called as the control lag. As like process lag, we have control lag. So total time for correction, the control lag. The time taken by like the process lag, we have time taken by control lag. Controller. Okay, so that is the total delay. Delay from change in control variable to correction in control variable. This is total time lag, and this total time lag consists of, or total time delay consists of process lag, that is the time taken by the process itself, and the control lag is time taken by the controller. People are now joining. What we can do now? So this is control lag. Next is dead time. What is dead time? Nothing happens in this. Okay? Though the error occurs and the corrective action is started, the time between this is called as a dead time. Okay? The time elapsed between the instant of error occurs and the corrective action first occurs. Okay, started. So in between this time, nothing happens. So no corrective action happens, and therefore this time is called as a dead time. Okay, for example, uh, it's a long pipe then. Okay, at the end of which a large vessel is there. Okay, the corrective action for the change of flow rate cannot occur instantaneously, though the controller starts action quickly. Okay, thus there is a period of time during which no effect is felt at the end of the pipe where the reaction vessel is connected. Okay, this is called as a dead time. So dead time also can have some effects on performance of the control system. So this is dead time. Next is cycling, right? So these are the oscillations. Cycling meaning oscillations. One of the problems in control is oscillation of the error above and below zero, especially in on-off control or two-position control. This is very important. This means that the control variable is cycling above and below the set point value. 60-degree temperature set, and sometimes it is 65, sometimes it is 55, and something like that. It oscillates about the set point of 60 degrees. So if the cycling is indefinite, it is called as steady state cycling. Here, what the factors to be considered are important factors: peak amplitude of the oscillation and the period of oscillations, error. Whereas, this, if the amplitude of this oscillation decays to zero, it is called as a transient error. Okay, it is steady state error or transient error. What are the important parameters or important properties to be considered here for this transient error? What is the initial error? Then what is the period of oscillation? And what is the decay time? Okay, so these are the important points to be considered if it is transient error. If these are continuous oscillations for a longer period of time, they are steady state error then. Okay. Then the controller modes. Okay. Choice of controller mode depends upon the type of process, product rate, and other industrial factors. Okay. Some processes, two position control will be sufficient, while other may require continuous mode controllers. Okay. So the choice of the controller for a particular process depends upon the type of process and the type of controller. So we must have the knowledge of types of processes and each type of controller, and then we can choose a suitable controller for a given particular process. Okay, in each mode, the percentage of the controller output. This we have already taken this formula. P controller output, percentage controller output, U minus U min divided by U max minus U min. We have already considered this formula. Okay, controller output is percentage full scale. So the P is the controller output at percent full scale. U is the value of output. U max is the maximum value of controlling parameter. U min is the minimum value of control parameter. Right. So the total range percentage controller output with respect to its total range is defined like this. Okay. Thus, if the percentage of output of the controller is known, then actual value of control variable can be determined because the controlled variable depends upon the controller output, and we know that the relation between controller output and the controlled variable, right? Suppose it is a level, the controlled variable is the level of the tank, and controlling parameter is the current, right? So we know the relation between level and current. Current range is 4 to 20 milliamperes, and suppose the level to be controlled is 1 meter to 10 meters. So 4 milliamperes will be corresponding to 1 meter, 20 milliamperes will be corresponding to 10 meters, and then this level is to be controlled. We know the relation between I and H, height in the tank, height, that is level in the tank. So we know the relation between H and I. Okay, generally this relation is kept as linear as possible, right? So if there is linear relation, then we can have the straight line equation for either expression between length h and the current I. Okay, so that is said here. In general, the controller operation is expressed as percentage full scale controller output is a function of error EP. The f of EP represents the relation between by which the controller output is determined. Okay. In some cases, P versus EP is shown to aid the definition. So graphical representation is there, and for what value of EP, what is the value of P, that is shown. That we will be discussing here for on-off controllers and other types of controllers. This graphical representation also. Okay, and the last parameter of the controller is whether the controller is direct action or whether the controller is reverse action. What does it mean? We know that the error can be positive or error can be negative. Say it is temperature control process. That case, error can be positive. Positive error का मतलब है, what does it mean? If we have a set point of 100 degrees Celsius, then error will be positive when the temperature is less than 100 degrees Celsius. So set point minus actual value gives the error, right? So set point minus 100 minus 90, that is 10 degrees Celsius positive error. Okay, and if the temperature exceeds 100, that is if it is 110, then set point minus actual temperature 100 minus 110 gives minus or negative error minus 10. Okay, so the manner in which the error will change the controller output can be selected according to the nature of the process. Okay, so the relation, okay, can be selected depending upon the nature of the process. Like for air conditioners or temperature controllers, etc., the changes are not that much sudden. Whereas in chemical industry, the changes in the control variable can be sudden, right? So in other industries also, level control or pressure control, the changes in control variable can be instantaneous changes, sudden changes. Okay, depending upon the process, we have to select the controller output then. When increasing values, see what is meant by direct and reverse is explained here. When the increasing value of error causes increase in controller output, एरर बढ़ता है तो कंट्रोलर आउटपुट भी बढ़ना चाहिए. Okay. If this is the relation, then it is called a direct action controller. Okay, as in case of liquid level. Whereas reverse action is its opposite. Then error बढ़ता है तो कंट्रोलर आउटपुट कम होता है, right? As like in temperature control, एरर जितना ज्यादा होगा उतना कंट्रोलर का आउटपुट कम होगा हीटर का, right? If it exceeds, then the switch should be off. Thermostat should disconnect the supply. So this is liquid level control is direct action, whereas temperature control of the heater, room heater, is reverse action control. Okay, so this is direct and reverse action. So in all, what we did, we discussed control system parameters like error, control variable range, control parameter range, control lag, dead time, cycling, controller mode, and reverse and direct action. Okay, so this was about the process and the controller. Now, actually, we'll be starting the types of control modes, right? So, what are the types of control modes then? Actually, we are starting this one now, controller modes. So, various types of controller modes are there. They are classified as basically discontinuous mode controllers, continuous mode controllers, and composite mode controllers. Okay, discontinuous, they have fixed the positions depending upon the error. They have fixed the positions. These are classified as two position, multi position. In multi position also, generally only three position controller is popular, not more than that, because it complicates the process also, because the final control element to be used has to be compatible with the controller for multi position. So generally not more than three positions are considered, but more than two, that is multi position, and third is floating mode control. Okay, so these are the types of discontinuous control modes. Next are continuous control modes. Okay, in this we have proportional control, we have integral mode control, we have derivative control, and composite we have PI, P plus I, PD, that is P plus D, and P plus I plus D. That is the ultimate or very popular controller in the industry. This is mostly used controllers are, these individual controllers are generally not used, right? Either on-off control is used or proportional control is used, PI is used or PID is used. These four controllers are majorly used in the industry. Okay, two position, proportional, proportional plus integral, and proportional plus integral plus derivative. Okay, so these types of controllers, this is the classification of the controllers. Let us take one by one. Discontinuous mode controllers. Okay, as we see, there are three types of discontinuous mode controllers. Then, okay, this is the basic mode having only two output positions depending upon the polarity of error. Okay, so this is simplest and cheapest and is used when its disadvantages are tolerable. Of course, there are certain disadvantages of this two position controller, and then that's why only other controllers were invented, right? They were discovered. Relation between controller output and error is written as P is equal to 0 for error less than 0, and P is equal to 100% for error greater than 0. Okay, so we have a set point. With respect to set point, If the error is less than 0, that is negative error, then output of the controller is 0. If the error is positive, that is if it is greater than 0, then output is 100%. Okay, like our temperature control, or like our temperature control in room heaters or electric iron, or what we call it as refrigerators, right? All these thermostat type temperature controllers are on-off controllers. Okay, so if the temperature is below the set point, the controller will disconnect the supply. Okay, whereas of the heater or refrigerator, whatever the equipment or process is, and if the temperature goes above, rather above the set point, then the controller will connect the supply to the heater and temperature will increase them. Okay, so 0 for EP less than 0 and 100 for greater than. Graphically, this can be shown in next slide. Okay, it is seen from this expression that if the measured value is less than set point, error is positive and output is 100%. If the measured value is greater than set point, error is negative. Okay, EP less than 0, output of the controller is 0%. Room heater is a common example. If the temperature drops below the set point, heater is turned on. Okay, if the heater is turned on, while if the temperature goes above the set point, heater is turned off. Okay, so this is the two position control. So let us discuss what is neutral zone. Okay, so this is very important in case of two position control. Suppose our set point is 100 degrees Celsius. Okay, say say not 100 degrees Celsius. Our room temperature, and we have a set point of room temperature to be 25 degrees Celsius. Okay, now the controller, whatever thermostat, whatever it is, okay, the controller output will be dependent upon the actual temperature in the room that is sensed. Okay, there will be a sensor sensing the room temperature, and that will be compared with the set point. Okay, so if the temperature, actual temperature sensed the value, control variable value, is exactly equal to 25 degrees Celsius, which is the set point, then controller output will be 0. Control will rather control will not have any action. But if it is 24 degrees Celsius, less than 25, less than 7 set point, then the heater will be on. The controller will connect the supply to the heater, and heater will be on. Okay. As soon as the temperature increases from 24 to 25, which is the set point, okay, and exceeds it, becomes 26, the controller will cut off the supply. As the supply is cut off due to environmental condition, temperature drops. Again, temperature goes below 25, and the controller takes action and switches on the heater. As the heater is switched on, then temperature goes above 25, say 26, and the controller cuts off the supply, and temperature again drops. Right. So, what is expected? Suppose the set point was 25, and the equation is something like this. What is the equation? P less than this. So EP less than 0, 0, and greater than 0, 100%. Okay. With this relation, if the set point is 25 and the controller senses that the temperature is 25.5, 0.0000001 degrees Celsius. The heater will be on, rather switch off. Due to environment condition, temperature drops and it becomes 24.999999, and it senses, compares with the set point, and uh, observes that the error is less than zero, right? Greater than zero, rather positive error. So it switches on the heater. So what happens is that the controller will constantly switch on and switch off, switch on and switch off, switch on and switch off. This is called a chattering, okay, or oscillating. So controller output will be continuously oscillating, okay, and this is not only harmful for the controller, it is harmful for the process also, controlled variable also, right? Process output also. So that's why what is done, a range of controlled variable is fixed, okay, above the, rather above and below the set point, so that unless and until the controlled variable value surpasses that range, the controller will not change its state from 0 to 100% or 100% to 0. Here, actually, if there was no adjustment like this that we discussed now, then the controller output would have been changing at this point like this and going this way and coming back again right this way. So it would be continuously changing its positions from 100% to 0 and 0 to 100%, because error slightly increases in positive direction, controller output is positive, and error slightly less than the set point, it is off then, right? So on off will occur. So to avoid that, a zone, okay, a range of the control variable is provided, a range of the error rather is provided, so that the controller output will not change its state from 100 to 0 or 0 to 100 unless and until that range is surpassed. Okay, so when the error is in positive direction, say from it exceeds the set point 0 error, right? So the control variable is dropping it here. So it will, the controller output will not change its state from 0 to 100 at this point. It will take, it will allow an error of delta EP, and after the error of delta EP, it will change its state from 0 to 100. So while coming back also, it won't change the output at exactly at 0 error, right? So it won't change at 25 degrees Celsius. That was our example set point. So it will come, it will allow an error of minus delta EP, and at that point only it will change its output. Controller will change its output from minus, rather 100% to 0%. So changeover from 0 to 100 is at this point, and changeover from 0 to, rather 100 to 0 is at this point. Ideally, it should be at 0 error, okay? But then that creates practical problems of chattering and will damage the process and controller, and therefore this range of the error is provided in which there will be no change of the controller output, and this range is called as a neutral zone. Practical implementation of two-position controller, there is an overlap as error EP increases through 0 or decreases through 0. This span or this range, in, there is no change in controller output. Okay, it is seen that until an increasing error changes by delta EP above 0, right, the controller output will not change state. In decreasing, the error must fall by delta EP, must fall by delta EP, this, okay, below 0, and controller output then changes its state to 0%. Okay, so total range becomes delta EP plus delta EP. It is 2 delta EP, right? So range of 2 delta EP for which the controller output does not change is called as neutral zone or differential gap. Okay, this is very important in case of two position controllers. This neutral zone or control differential gap is purposely designed above certain minimum quantity to prevent excessive cycling. Okay, and this is actually an instrumentation system. This type of property is called hysteresis. Okay, hysteresis in other systems is undesirable, but in on-off control, it is purposely added. Okay, this zone is purposely added. So this is desirable hysteresis, right? Like in gears, hysteresis in gears. Two gears are uh, contacting each other. They are rotating. Okay, so one side of the tooth of one gear, driving gear, is connecting the other one side, a specific side of the tooth of driven gear. So they are in contact and they are rotating in clockwise direction. Suddenly, if the rotation direction of rotation changes, then there will be a small span when there will be no rotation at all because the driving gear opposite side of tooth side has to connect the other side of driven gear. So there will be a gap between the tooths, right? Gap between tooths of driven gear and drive gear, so that during that period of time there is no change in output. Okay, so this type of property is called as hysteresis, and that is actually undesirable. But in case of on-off controller, this is purposely added to the system so that excessive cycling or oscillations will not be there and it won't damage the controller and uh, process, right? Let's have an example for on this one. Okay, excuse me. What is given? Say, read the problem. I'll explain and you will solve it. Huh? A liquid level control system is there. The tank is there. Okay, and level of the liquid in the tank is to be controlled. The height or level, okay, that changes from 2 to 3 meters. This is the range of the control variable. 2 meter to 3 meters, right? So minimum is 2 meter and maximum is 3 meter. So, and this displacement, our transmitter is converting into, okay, this control system is converting this displacement of height change, level change from 2 meter to 3 meters into 4 to 20 milliampere range, right? This is the control signal there, controller output. Now, a relay serves as a two position controller. It is on-off controller. Relay is either on or either off. Okay, so 4 to 20 milliampere current is given to the coil of the relay coil, and the contacts of this relay coil will be opened or closed depending upon whether the current is sufficient or current is not sufficient. That is given later. Okay, relay serves as a two position controller to open or close the inlet valve. Okay, inlet valve is suppose say solenoid controlled solenoid valve, and that the opening or closing of the valve is decided by the opening and closing of the contacts of the relay. It is said that the relay closes at 12 milliamperes and opens at 10 milliamperes. Okay. So what is to be found out? Opening and closing is given. Okay, where the relay will be closing and where the relay will be opening. It is given, right? So 12 milliampere is the highest level corresponding to, and 10 milliamperes is the lower level. Okay, find the relation between displacement and level current. It is given that the relation is linear. This is important. Huh? When the problem is given, what is the type of relationship? Okay, so find the relation between displacement level and the current and the neutral zone or differential gap in meters. Okay, so what to do? Since the relation given is linear, we must assume a straight line equation. What is a straight line equation? Y is equal to mx plus c. Y is the displacement and x is the dependent variable, that is current, right? So level 2 to 3 is y, right? Whereas 4 to 20 is x, right? So y is equal to mx plus c. We will have two equations. For y is equal to 2, corresponding current is x is equal to 4 milliamperes. For y is equal to 3 meters, corresponding current is, we have 20 milliamperes. So we will have two equations. So y is the height, whereas x is the current I. So this is the relation between h and I. Okay. So y is equal to mx plus c. It means that h is equal to some k into I plus c is h0, initial value of h. Okay. So h is equal to ki plus h0 is the relation. So what is the question is to find out actual relation. That is, we want to find out the value of k and h0, right? So can you find, forming two equations, find the value of k and h0. Write down the equation as h is equal to k into I plus h0. Are you writing? Please. Are you there? Substitute the values of h and I, form two equations, solve them and find k and h0. Tell me the values. Anyone? Are you doing? Solving it na. Answer anyone, please. Please answer. Answer, please. Neha, Devshri, Prajwal. हाँ, कितना है एजाज? What is the value of k? What equation I told was h is equal to k into I plus h0. So form two equations. H has a range of 2 meters to 3 meters. So, and current has a range of 4 to 20 milliamperes. So 2 is equal to k into 4 plus h0 and 3 is equal to k into 20 plus h0. Solve and find out k and h0. Put the value of k and h0 in equation and that will be the relation that we want to find out. Okay. So what relation did you get then? Solved it with a simple equation. See, range of the displacement level is given as 2 to 3 meters. Range of the control signal is given as 4 to 20 milliamperes. Type of controller is the relay, on off or two position control. Relay closes, that is at higher level, 12 milliamperes. Relay opens, that is the lower level, at 10 milliamperes. Okay. Relation between level and current is given as linear. So let this relation be expressed as h is equal to ki plus h0. Putting these values of 2 and 3, 4 and 20, we get 2 is equal to k into 4 plus h0, 3 is equal to k into 20 plus h0. And solving this, we get k is equal to this and h0 is equal to this. So relation that is to be that is asked. Okay, find the relation between displacement and the current. So relation is h is equal to 0.0625 into I plus 1.75. Okay, and what is the next part? Neutral zone that is to be found out. Okay, so that we will find out from these two values. Putting these two values, we will find h and difference between higher level h and lower level h will be the neutral zone. Understanding or not? This corresponding to higher level, this corresponds to lower level. Okay, so difference between the levels, unless and until this difference is overcome, the output of the controller will not change, right? So let's see. Relay closes at 12 milliampere, which is high level. So Hs is equal to k into I plus 1 H0. So k we have found out, that is 12 I plus 1.7. This comes out to be 2.5 meters. Relay opens. This is at 10 milliamperes, which is the low level. So HL is equal to this plus this one. So 2.37. So range of the level for which the controller output will not change is higher level minus lower level. So HH minus HL, 2.5 minus 2.375. So the neutral zone for which the output will not change is 0.125 meter. Okay, so this is what is the neutral zone then, right? Let's move further then. Now, what is the graphical representation of this? Okay, and what are the advantages, disadvantages that we will discuss of two position control? The process control under two position mode has continuous oscillations in control variable because it produces such oscillation. It is a property because unless and until the control variable value exceeds or drops, exceeds above or drops below the set point, controller won't take action, right? So control variable has to exceed the set point or drops below the set point, then only controller will give output. Okay, it has the basically inherent property like that. So there will be what we call it as overshoots and undershoots. Okay, so initially the controller output is high because the level was 0. Okay, so controller output is high, level increases, and it exceeds the set point of. Can you see this is 120? It exceeds 120, right? Temperature it is not level. Sorry, temperature of 120 degrees is exceeded, and at that point the controller output becomes 0, right? The heater will be switched off, and then the temperature will decrease. Okay, temperature will decrease, and it goes below the set point. Okay, it goes below the set point, and as it goes below the set point, the heater will be on, right? The controller output will be high, and this again continues. Then it drops below, it exceeds, drops below, exceeds, drops below, exceeds the set point of 120 degrees Celsius. So overshoots and undershoots will be there like this. That is not avoidable. Okay, this is non-avoidable property of this one, two position controllers. Okay, so what are the advantages then? These oscillations will be bound to be there. What are the advantages and disadvantages then? Two position controller is very easy to design, that everywhere we use it, right? Especially for temperature control. Most of the devices are using this, right? Where the exact and sudden changes of temperature are not to be controlled, then generally the controller type of controller used is the on off or two position controller, right? They are cheap rather than other types of controllers that we will discuss, proportional, and especially PID controllers are very costly, right? Unless and until process demand is like that, very accurate control, we won't go for PID, right? So as far as possible, the cheapest controller is on off or two position controller. Okay, they are used where precise control is not necessary, as we saw, right? Where overshoots and undershoots are tolerable, then only this type of controller can be used. Okay? And they are useful in slow changing systems, okay? Like level control in large tanks and the temperature control, right? So in such systems, two position controls have an advantage over other types of controllers. What are the disadvantages? They are either 100% or 0%. Okay? This can cause considerable overshoots and undershoots. That is a disadvantage actually. They perform poorly when controlling rapid system fluctuations, hence provide poor control and are not recommended for chemical processes where the sudden changes in the control variable are possible, right? Neutral zone or hysteresis. If this is not provided, they can damage the actuators and pumps due to rapidly switching them on and off. So that was the major disadvantage, and neutral zone has to be provided deliberately. The hysteresis gap, differential gap has to be provided. Otherwise, the final control elements and the process, like actuators and pumps, will be damaged. Okay. Even though hysteresis is used, there will be a constant error of that delta EP will be there on instance, such as room heaters, air conditioners, level control of large volume tanks, etc. etc. Right? So these are the two position controllers. Now, multi-position controllers. But the time is over. We'll discuss multi-position and floating control modes in next lecture then tomorrow. Right? Let me mark the attendance. Okay, attendance is marked. So what we'll do, we'll continue in the next lecture then, right? Multi-position, that is three position controllers, and the floating point or floating controllers, and then other types, continuous mode, P, I, and D controllers, right? So let me stop here only. I'm ending the meeting. You can leave now.